if you have problems with the midterm, grading issues, things that have been overlooked, situations of that kind, it's a big class, and it's certainly possible that all of those things have happened. And the other thing you should also look at is whether your points have been computed correctly. It's been done in Excel, but still, if everything has been added up correctly. If you have any of those troubles, write a note in the exam and give it back to me at the end of class. I'll pick it up, and since different problems have been graded either by me or by Ali, we'll distribute it among them ourselves and get back to you. To just give you some perspective, last year's average I looked up was 67 out of 200, and this year's average was 82 out of, or was it 82? 87 out of 150. So you should feel happy that the course, that the, either I set up a easier exam, or you guys are much better than last year's class. The more charitable way of looking at it would be that you guys are much better than the last year's class. One of the problems with that is that the folks who are kind of far away from 87 don't have much to sort of blame me for. I mean, last year's class would have blamed me and said it was a tough exam. This year's class, since many of you are doing very well, the highest was, 124? So anybody below 50, I would say, is at a point where they should start questioning what's wrong. It could be that they panicked. It could be that, you just didn't understand what's happening in class. If you simply panicked, are not used to taking exams, just come back from working, things of that sort, I can understand that is 3 weeks. It's the moment you start coming into this class, the first thing that falls on your head is this midterm, and you blink an eyelid and you get your scores back, and now next Thursday is the final. So it's a short time, but if what's bothering you is not so much the time issue, but the fact that you're not understanding material, that's something that's worrisome, and you should either talk to me. I'm here Tuesday, Thursday until at least 7 o'clock, and you're welcome to stop by anytime, or talk to Ali by email, go to his office hours, recitation, whatever. We want to make sure that you learn the material. As regards the exam taking skills, that's just something that you'll have to learn on your own. The next announcement is about the final, which is going to be next Thursday from 2 to 5 p.m. and we'll split again the same as we did before, which was A through whatever it is. I forgot my email, so I'll find out. It'll be split between this room and the C.P. Davis auditorium. What else? Do I need anything else? Any other announcements? Oh, 4 people have not picked up their exam books, so after class, pick them up. And they're with me now. Any questions about the midterm? Anything that, any administrative issues?
When do we have the classes?
We have it till Tuesday. Yes. So Thursday morning there will be no class. Like I said last time, I will be available here on Thursday morning. So if you have trouble with anything, the full entire morning I'll be here. So you can talk to me. On Wednesday, I'll probably either by this Thursday or definitely by next Monday, set up a practice exam, and Ali would go over it on Wednesday.
And the content, everything will be specified over there?
Yes, the content will be specified, and the way Ali sent an email last time, he will also specify the exact sections of the textbook which you're responsible for. And we'll also tell you explicitly what are the material that you're responsible for. And everything before the midterm you are still responsible for in the final. It's a cumulative final, but there won't be any direct questions on LP. For example, problem number 1, which was essentially LP geometry, don't expect any problem of that kind. It won't be there. But somewhere along the line you might have to use some linear programming, so that's game. Okay? Any other questions before I begin? So the two things that are left over in this course is integer programming, and I'm hoping to cover whatever I want to cover by today. So starting this Thursday and next Tuesday, we'll be doing dynamic programming, which is the last part of the course. Okay. All right. So last week we started off by looking at a very simple integer program, a 0-1 problem which basically was choosing between 3 different kinds of mutual funds and saying, well, if you don't choose a particular mutual fund, you have to somehow make sure that the investment in that mutual fund is 0. Here we are looking at a slightly different problem, but it's basically the same. We're looking at a problem which has piecewise linear costs. So if on the x-axis here, I plot the number of parts ordered, then the cost is a fixed cost of 10 units, and then followed by the first 10 pieces cost 5 per unit. That's up to the first 10. The next 25 cost 4 units. So that's 35 here. And the next, so the slope here is 4, the slope here is 3. Is that correct? Yes. And then for operational reasons, you assume that you're not going to order more than 200. And it'll become very clear why one has to have this bound. A priori, you might want to think that why do you need this bound? It'll become very clear why you need it in a moment. But for now, just assume that that for some reason this 200 bound is given. And what we want to figure out, so out here on the y-axis is the cost of ordering, f of x. And what we want to do is we have a constraint of this kind in our problem, f of x less than equal to b, and we want to translate this into some constraint which looks like A transpose X plus B transpose Y. Oh, I need to mute this thing. Something that we'll put in some extra variables less than equal to b. So what I want to do is, instead of having a nonlinear function, this is a nonlinear function, I want to have a function that looks linear, but perhaps uses some 0, 1 variables. It's not quite a linear function because the moment you start putting 0, 1 variables, you cannot use linear programming anymore. But it just has a structure of a linear function. Why do I care about the structure being linear? Because in the afternoon, we'll talk about methods of solving these integer programs. There it becomes very necessary that this starts looking like linear. Okay? So as I began doing it last time, what we would pretend is as if we are ordering from 3 different suppliers. I just extend these straight lines forward. And so we now have 3 different suppliers, and their supply costs, or let's say from supplier 1, the cost is K1. What's K1 there? 10. 10 plus 5x. From supplier 2, the cost is going to be, what is it? 20 plus 4x. And from supplier 3, the cost is going to be 55 plus 3x. Okay, so I just extended the 3 lines, and you ended up getting these things. And I know that it's profitable for me to order from supplier 1 as long as 0 is less than x is less than equal to 10. I'm going to order from supplier 2 if x is, it doesn't really matter, so I'm just going to put x is between 10 and 35. And at 10, it doesn't really matter whether I get it from supplier 1 or from supplier 2. And this one, the third one, is competitive between 35 and 200. Again, at the boundary points, it doesn't really matter whether I go for supplier 3 or go for supplier 2. Okay? And what I want to do is somehow introduce 0, 1 variables, maybe some extra variables, such that this choosing between supplier 1, 2, and 3 is automatically done by these variables. And what I'm going to do is have 3 different variables. I'll call B1 equal to 1 means order from supplier 1, and 0 otherwise. If B1 is equal to 1, I'll order from supplier 1. If B1 is equal to 0, I don't know where I'm ordering from. I don't have any information. Similarly for B2, the same definition, except now it's for supplier 2, and B3 is the same definition except it's now from supplier 3. Okay. Now what I want to do, if B1 is equal to 1, meaning I'm ordering from supplier 1, what do I have to ensure about my x? X has to be less than equal to 10. So x must satisfy what kind of constraints? 0 is less than equal to x is less than equal to 10 times b1. Right? The amount that I would order from supplier 1 has to be between 0 and 10. Let's put an x1 there, meaning the amount that I ordered from supplier 1. What about for supplier 2? If I order stuff from supplier 2, what kind of bounds do I need to have? Now, how am I going to write that using this variable b2? If b2 is equal to 1, what must happen? So we want x2 to be less than equal to 35 times b2. But what about the one at the bottom? Do we want it 0? 10 b2. And what about the order amount that I ordered? So in the case when b2 is equal to 0, what does this give me? 0, which is fine. If b2 is equal to 0, then the amount that must be ordered from supplier 2 is equal to 0. Similarly over here, if b1 is equal to 0, the amount that I ordered from supplier 1 is equal to 0. What about b3? What about x3? What are the bounds do I need? That has to be less than 200 times b3 and greater than equal to 35 times b3. And that's why we need this upper bound. If b3 is equal to 0 and I did not have an upper bound, I cannot force x3 to be equal to 0. If I'm not producing anything from supplier 3, and suppose this upper bound wasn't there on my problem, then I cannot force x3 to be equal to 0. I need the upper bound in order to make sure that x3 is equal to 0 when b3 is equal to 0. Okay. So I've just restated all the stories. So what is the total number of units that I order? What is the total x? It's x1 plus x2 plus x3. The total number of units I order from supplier 1 plus the number from supplier 2 plus the number from supplier 3. I've made sure that I order only these quantities. Now what's the one constraint that's missing still in my modeling? What do I have to still impose? b1 plus b2 plus b3 is less than equal to 1. What does this imply? What does that constraint imply in words? You can at most order from one supplier. You cannot order from two or more suppliers or at the same time. Okay. So I have a representation for the number of parts ordered using these variables b1, b2, b3. Now I want to write out the cost. So what is the cost now? What's f of x? Now instead of just having f of x, now I have f of x1, x2, x3, the three variables that I have created, b1, b2, and b3, the three other variables that I have created. Using these 6 variables, how can I write the total cost? Which one?
b1 b1 plus 5x1.
So its first one is 10, using this thing, 10b1 plus 5x1. What else? Plus 20b2 plus 4x2. And finally plus 55b3 plus 3x3. So notice what we did. We had these 3 costs, which were essentially all we have done in this whole construction is that we introduced these variables b1, b2, b3, which are choosing which piece this is coming from. Once I know what piece the thing is coming from, the cost is coming from, the total cost is linear in there. And therefore, I can represent it as a linear function as long as I have these extra variables. I have these extra variables b1, b2, and b3 which take only values 0 or 1. I could not have done this if b1, b2, b3 were allowed to take any value between 0 and 1. If they were continuous variables, this is not possible. This is possible only because these are discrete variables. And once I have introduced these discrete variables, I can split up my range into 3 pieces using these discrete variables. So these discrete variables are playing 2 roles. First, they're allowing me to choose a piece, and also they are picking up this fixed cost. If I order something from a supplier, I have to pay a fixed cost. That's been picked up by that 0, 1 variable. If it's 0, I don't pay a fixed cost. If it's 1, I do have to pay a fixed cost. So it's this part here, the ones that are coming from the 0, 1 variables are the fixed cost. The ones that are coming from the x variables are the continuous or the variable cost. All right? The same story happened with the mutual funds. The only difference here is that it looks different from the mutual fund example in that you have just one function, but it's similar to the mutual fund example in the sense that you basically have to pick out the 3 pieces. Once you know how to pick out the 3 pieces, everything else falls in place. Questions about this example? Yeah?
How do you solve it?
How do you solve it? In Excel, you can solve it very simply. Just put them to be binary. But really, the way it is solved in practice is what you do is relax the binary constraints. You put this, the reason why we are after, so let me just go a step further, we'll come back to this in the afternoon. So we had started with this constraint, f of x is less than or equal to b. We replaced that, let's not put a b here, some cost c. We replaced that with this constraint. This one is less than or equal to c, x1 plus x2 plus x3 is equal to x, and b1 plus b2 plus b3 is less than or equal to 1. So all of them now look like linear constraints, except that you have this extra constraint which says that bi lies in the set 0 or 1. It can only take values 0 or 1. When you're trying to solve this, what you do is that you first relax this condition to be this interval. That bi can take values anywhere between 0 and 1. That's a relaxation. You'll find a solution, and that solution will typically have b's fractional. You'll end up getting b's that are fractional, meaning that take value strictly between 0 and 1. Then you have several different techniques. One thing is to do some kind of a rounding. And in the homework that will be given to you on Thursday, you can easily see in certain examples you can round things. You can say if bi is less than a half, make it 0, and bi is greater than a half, make it 1. But that doesn't work always. So then you have this other technique called branch and bound, which is, the way to think about it is intelligent enumeration. You basically enumerate all possibilities, but do it intelligently such that along the way you keep enough information such that you don't have to enumerate all the way through. A third possibility is cutting planes. All of these things, in order to tell you how to solve these, we'll have to teach you another semester-long course on just integer programming, and in fact it's done in this department. So what I'll do is basically touch upon this, give you an idea how this works. In most of the cases, there are built-in algorithms that will allow you to solve this using any kind of solver. Whether it's Cplex, whether it's SAS, whether it's Solver, they have some of these things built up. It will give you, our focus would be more on trying to use modeling rather than trying to show you how to solve these in practice. Okay? All right. The next very important model that we'll come back to again on Thursday and try to solve it using dynamic programming is the so-called knapsack problem. And there's an example there, but generically speaking, here's what the story of a knapsack problem is. So you've got n objects. These objects have certain weights, W1, W2, up through Wn. And then you've got, these objects have certain values, V1, V2, up through Vn. And what you want to figure out is you've been given a knapsack, or a backpack, or whatever you want to call it, which can carry up to weight W. And the knapsack problem basically boils down to which of these objects should you pick so that you maximize the value subject to the weight constraint. You've got a fixed weight, you can carry only up to capital W weight. These are the values, those are the weights. So the problem simply is to maximize the sum of I going from 1 through capital N, Vi xi, such that summation of I going from 1 through N of Wi xi is less than or equal to capital W, and xi takes values between 0 and 1. Not between, sorry, it takes values 0 or 1. So if I write out this optimization problem, what is the interpretation of xi? xi1 means what in words? I'm taking object I, and 0, it means otherwise. Okay? So all this constraint is telling me is that if I pick up a particular object, then I have to pay the cost of carrying its weight. If I don't pick up that object, then I don't pay the cost. And I cannot use fractional objects. I cannot pick up fractional objects. All right? So I can either pick up the object or not pick up the object. And if I do pick up the object, then I get a value for it correspondingly up there. And the problem boils down to is how do you pick objects such that you maximize the value subject to the weight constraint. All right? Okay. Now, just to give you a preview of how these things are solved, suppose I were to take this and relax it. So let's make certain assumptions. First of all, let's make the assumption that each of the values is strictly positive and each of the weights is strictly positive. Suppose. Doesn't have to be that way, but suppose this is the case. And in that situation, under that assumption, suppose I relax this to xi between 0 and 1. Okay? Then what's going to be the optimum solution? What do you think you're going to do? Suppose I tell you that the values are strictly positive and the weights are strictly positive. And now you can take fractional objects.
You look for Vi divided by Wi that's highest.
Yes?
Take it as much as you can, and then you...
Exactly. So what you do is you arrange Vi over Wi in decreasing order. And start filling up the bag.
Are you also optimizing on space here in the sense that obviously it's going to carry some more of the space as well?
No. So what Vi over Wi tells you is what is the most bang for your buck. For unit weight that you're putting in, you first pick the object that gives you the most value, put it into your bag, and keep going. Right? So you are comparing the two things. So if Vi is really high but corresponding Wi is very high, then you don't like that object. You have to look for the ratio of those two things. However, discreteness causes a problem because it may be possible that you are able to just fit in one more object which is not as competitive as something else, which you can't fit completely. But one thing to keep in mind is that if you relax this, how many fractional points can you get? What is the worst number of fractional objects will you pick up? 1. There's at most only one variable that has to be rounded. All the other variables will be either 0 or 1. So irrespective of what n is, n could be 2000. I automatically know there will be only one variable that's going to be fractional. So this implies that the greedy solution, this is called a greedy solution because we really didn't do anything intelligent optimization. We know that this is optimum, but it's sort of a very myopic way of solving it. So this will ensure only one fractional. More generally, you can prove that the number of fractional quantities is sort of connected with the number of constraints that you have here. If you have 2 constraints, you'll end up getting 2 fractional quantities, and so on. So if you have a small number of constraints, typically the number of fractional quantities is small. So this strategy of first relaxing the 0, 1 variables, solving a linear program, either by a greedy method, as we did here, or by actually solving the linear program, ends up giving you a solution which doesn't have too many fractions. And then we can start from that solution to try to round or try to get better branch and bound or so on. That's just looking forward. Here, I just want you to keep in mind that this is actually done very easily, and we'll show you how this can be used to get fast solutions for knapsacks. Yes?
This is not the optimal solution.
This is not the optimal solution for the IP, but indeed it's the optimum solution for the relaxed problem. Yeah. It is not the optimum solution for this IP. So you have to start from, you have to do something to get the optimum solution for this. But the fact that there's only one fractional point makes my life a little simpler. Because suppose at the end of the day, so this brings us to another good question. Suppose I solve this problem and it so happened that all the xi's were either 0 or 1. I was lucky. It just fit in exactly. Then I know that's the optimum solution. Right? Because I solved the relaxation, I allowed it to between 0 and 1, either other than just being 0 and 1. I found a solution which satisfied the old constraint. That must be optimum. So all I'm trying to do is from that point where I got the fractional points, I have to either check, do I put the object in, the last fractional one, or do I not? And consider those cases and have a decision tree going forward, but do it intelligently, and I can get a better solution. I can get the optimum solution. If there were, say, 5 of them fractional, then I've got a problem. I'll have to look at, right at that point, my decision becomes 2 to the 5. So it's easier if you have lower number of fractionals than if you have a larger number of fractionals.
Decision is not only to put it or not to put it.
Yes, that's not just a decision.
Here you can just change everything.
Sure. The hope is that when you start from that point, it's close to optimum. It's definitely not guaranteed to be optimum, but if I have to just make 2 choices, I can use that, I can leverage that to make my life faster. But it's not definitely going to be optimum. Definitely the case.
Another thing
Yes.
about the fact that you have only one fractional, does that follow from somehow choosing the W? In the sense that you said that there's only one. How does that follow?
Oh, because the thing is, the greedy algorithm, we know that this is optimum. So what are we going to do? We're going to start piling up these objects in decreasing order of Vi over Wi. So you've put in object 1, object 2, object 3. At some point, I can not fill up. I'll start putting the object, and I can't put the entire object. So it's just going to stop at that point. So that last object is going to be fractional. I might be lucky, and I fit in exactly the right number of objects. But in general, I'll be unlucky, and I'll put some fractional amount of the last object. But there's only one object that can have that. But if I had 2 constraints, then I might have to play with 2 objects to fill up the constraints completely, and I'll end up having 2 fractional quantities, and so on. Okay. All right. The next generalization of this, so here knapsack problem has only one constraint. The next step further is something called a capital budgeting problem, where you have several different weights. Each object comes with 2 different kinds of weights. And you want to make sure that they individually satisfy the separate constraint. Such a problem with multiple constraints is called a capital budgeting problem. It's basically a knapsack, but multiple constraints. Typically, these multiple constraints come from different time units. So this could be a constraint in period 1. This could be a constraint in period 2. And here's an example for this problem. This is an example taken from NASA's budgeting decisions. Probably a more relevant example would have been whether to fly the space shuttle or not, or maybe a more morbid one, whether to fix those tiles or not. But in any case, this is a more ancient thing. This was, and there is an Io. I don't put it up there. So this basically, Io is a moon of Saturn, and there was this lander that was going to go to Saturn, and what they wanted to do was figure out which of these 4 different projects or 4 different activities should NASA fund. Object number 1, or activity number 1, was a communication satellite. It required $6 million, billion dollars, no, it should be million, $6 million, and it gave you a value of 200. So the value is sort of like, it's also into this value figures in both the actual value of the activity and also the probability of success. And that's why you end up getting that a Uranus sort of IO ladder, which might have more intrinsic value, but there is a chance that it will fail before it reaches IO, so the effective value that you have is low. Doesn't really matter what's happening. So these are the 4 different activities one can do, and there are 2 different timing periods, or 2 different project periods where you have to spend money. The first 5-year period, this is the amount of money that's required, and the second 5-year period, some other amount of money is required. So for this particular example, the capital budgeting problem would be, you want to maximize 200 times x1 plus 3 times x2 plus, what is it, 20, 30, 20. 20 times x3 plus 70 times x4, such that, now comes the constraint for period 1, 3 times x2 plus, or 6 times x1 plus 2, 3. 2 times x2 plus 3 times x3 must be less than or equal to 10. And then the next one says 3, 5, and 5. So 3 times x2 plus 5 times x3 plus 5 times x4 must be less than or equal to 10. And each of the xi's has to be between in the set 0 or 1. Okay? So there are the other 2 tables that we have to deal with in a moment. So far all I'm saying is I'm looking at these 4 different projects that have to be done. I have a total budget of 10 available in the 2 time periods, and I want to make sure that the collection of objects that I choose to put into my bag, or the projects that I decide to do, are satisfy the budget constraints in both periods. And that's why you end up getting 2 constraints. This is for period 2000 to 2004, and this one's from 2005 to 2009. Okay. Now let's deal with these 2. This one says that if I decide to do 1, then I can't do 4. 1 and 4 are mutually exclusive. 4 cannot be done with 1. How do I put that constraint into my program here? Into my 0-1 binary program or integer program? x1 plus x4 equal 1? Less than equal 1. I don't want it equal 1 because I don't want to force ourselves to do any of these projects. I just want to make sure that if x4 is done, then x1 must be 0. If x4 is equal to 1, then x1 should be equal to 0. What about this one? This one says that the Uranus orbiter 2000 depends on 3. If 3 is not done, then 4 cannot be done. x4 less than x3 or x3 less than x4? Well, okay, whenever I say less than, it's going to imply strictly less than equal to. I'm not going to put any less than or greater than sign without an equal to. Okay, so let's see what's that's going to be. x4. So, okay, so I'm just going to put x3 here and x4. And let's decide which direction we want to go. x3 has to be greater than x4? What does that mean? It means that if I did x4, if I choose to do x4, then it must be the case that x3 is equal to 1. I'm forcing, by doing x4, I'm forcing x3 to be equal to 1 because 4 depends on 3. If 4 is being done, then 3 better be done. But the other way around is, but if x3 is equal to 1, meaning I did activity 3, nobody is forcing me to do activity 4. 4 requires 3, but 4 does not mean that, 3 does not mean that 4 must be done. So that's allowed here. x3 equal to 1, x4 equal to 0 is possible, x4 equal to 1 is possible. And finally, you just have xi in 0, 1. All right. And, let's try another thing. Let's say if you wanted to put an extra constraint here that at most 2 out of 4 must be done. how would I put that constraint into my problem over there? Sum is smaller than 2. So sum of the xi's, I going from 1 through 4, has to be less than or equal to 2. Yes, question?
What if 4 required 2 and 3?
Okay, let's try this. So let's put so suppose you had a constraint this, that 4 requires 2 and 3. How would we do this? That's and just means a conjunction of constraints. Any number of ands mean you just put constraints after constraints after constraints. This would simply mean that if x4 is equal to 1, then it better force x2 to be equal to 1. And if x4 is equal to 1, then it better force x3 to be equal to 1. What if we had this? 4 requires 2 or 3.
Maximum of
Max is not linear. Don't want max. x2 plus x3. Okay. Every time you have an or, you add up those variables. Every time you have an and, you put multiple constraints. Another way of doing this, these two constraints could have been this. 2 times x4 is less than or equal to x2 plus x3. You just add them up. It's the same thing. Okay. So 0, 1 variables. So far, in terms of use of integer programming in financial applications or decision applications of these kinds, 0, 1 are probably the most useful variables. Integer variables are also used, but then it sort of becomes generic. Then you're just saying that that constraint is coming from the fact that you can't buy continuous amounts. You're just buying discrete amounts of objects. There is no new modeling idea. Whereas when you're making decisions of this kind, whether to take an object or not take an object, it allows you to put in logical constraints. All of these constraints were logical constraints. It allows you to choose between objects. And most of the use of integer programming comes from this aspect, the logical aspect and the choosing aspect. And therefore 0, 1 is probably the most interesting modeling quantities. Let me go through a few more models. In the afternoon, I'll show you an application, maybe 2 applications of using these models in constructing an index fund and also in doing some mortgage-backed securities. Okay. The other sort of generic setting in which things come up is, so let's do it in the context of this example. There are certain kinds of constraints that have names. The reason we have names for these constraints is because they are very well-studied constraints, and there are techniques for solving a problem which has only these 3 types of constraints. There are better techniques available, faster techniques available. But as far as modeling goes, it's sort of not a very interesting one. So an example of a set covering constraint is the following. At least one of activities 2, 3, and 4 must be done. That's an example of a set covering constraint. In this particular case, the set J is going to be 2, 3, and 4. And what we are saying is that at least one of the xj's, so at least one xj for j in the set J must be 1. Which translates to this constraint. Sum over j in capital J, xj must be greater than or equal to 1. So in words, it's actually a pretty simple constraint. All you're trying to say is cover that particular set. as long as you pick one from the set J, you're covering that set, so you're happy. Sometimes these kinds of constraints come up in diversification. You are looking at various asset classes. You want to make sure that you're exposed to every asset class. And these could be, equities which are low, medium, and large caps, and then you want to make sure that at least one of them is picked up. An example of set packing is typically at most. Instead of at least, you have at most. And we already saw that example there. So this third constraint over there, this constraint here is a set packing constraint. Out of the 4 objects, at most 2 must be picked up. Here is another example. At most 1 activity out of 2, 3, 4 must be done. So this just becomes less than equal to 1. And if you have a constraint which is both a set covering constraint and a set packing constraint, you get a set partitioning constraint, which says that exactly 1 must be picked up. You don't have the option of choosing more than 1. You don't have the option of choosing less than 1. Exactly 1 has to be picked up, and that's called a set partitioning constraint. The names are not that relevant for the purposes of this class because we are not interested really in figuring out how to solve these problems. We are only interested in how to model these problems. The names or labels are more interesting when you try to solve them, because if you have these kinds of constraints, then you end up getting better techniques to solve them. Okay, so let's use this idea to solve another interesting problem. It just gives you a new technique. So let's say that there's a OR department that's planning to buy codes, 4 different kinds of codes to provide different kinds of capabilities: LP capabilities, IP capabilities, and nonlinear programming capability. So code 1 is the cheapest code, but it only provides LP. Code 2 and code 3 give you 2 different kinds of techniques: LP and IP, LP and NLP, and those are the costs. And code 4 is the most expensive one, which covers all 3 activities. Now here's the problem that we want to solve, and we'll use the set covering packing ideas. What we want to solve is that we have a budget of 12 units. And what we want to do is maximize the number of different capabilities, meaning the number of different types of algorithms that we can solve, the number of different capabilities that we have. It's a little toy problem. Let's not focus too much on trying to solve this just by looking at the numbers. Let's try to model it. So I have 3 different kinds of capabilities here: LP, IP, and NLP, and 4 different kinds of codes that I can buy. And I want to make sure to maximize the number of different capabilities. So how would I go about modeling this problem? What are the variables that I would use here? So let's have one set of variables. Let's call them xj. This is equal to 1 means buy code j, and 0 it means otherwise. So using these variables, I immediately know that my budget constraint would give me that 3 times x1 plus 4 times x2 plus 6 times x3 plus 14 times x4 has to be less than equal to 12. Immediately I know that x4 has to be equal to 0 looking at that constraint. But let's not worry too much about those things in a moment. Okay, now how do I write my objective using these variables?
Maximize the sum of.
I can't simply maximize the sum. So you need to have some idea of saying, so if I buy x4, I've maximized it already. I have all three capabilities. So I somehow have to capture the fact that buying 1 actually doesn't give me as much as buying 4. They don't have the same weight. So how do I capture that in an objective function? Let's put in extra variables, and maybe we can resolve those variables down in terms of those kinds of constraints. Let's define a new variable yi is equal to 1 if capability I exists, and it's 0 otherwise. Right? And then I'm sure that this is what I want to maximize. I want to maximize sum of yi, I going from 1 to 3. These are the variables that I'm interested in. Whether if yi is equal to 1, then I have that capability. So far I've not done anything interesting. All I said was I created xj variables which says, do I buy code? So what are the two things that I have to decide? The two things that I have to decide is whether I have a code and whether I provide the activity. And all I've done is just created new variables for both of them. And yes?
If you were to add, if you were to have two codes which do LP, wouldn't this formulation mean that you would get 2 times the value, but really you would only get 1?
Yes. So I still haven't figured out how to connect the xj's and yi's. The only thing I'm saying is I'm just dumbly put down 2 sets of variables. One set of variables just tells me, do I buy the code or not? And using these set of variables, this is writing out the constraint for the budget is very convenient. I just multiply it by their cost and less than equal to 12. Now I defined another set of variables that just keeps track of whether I have the capability or not. And if I do have the capabilities, then I know this is what I'm maximizing.
Then we just write y1 more than x1.
Right. So now we have to connect the y's to the xj's. So if my y1 is equal to 1, meaning that I have provided the LP capability, what must that imply?
y1 is bigger than x1, and y1 is bigger than x2.
Y1 is bigger than x1?
That's because x1 can be 1 or 0.
X1 could be 1 or 0, but does x1 have to be? It's the add all the 4. All I care about is that if I'm forcing y1 to be 1, meaning that I'm deciding that I want LP capabilities, then this better be x1 plus x2 plus x3 plus x4. One of them has to be 1. If I want to get LP capability, then at least one of them has to be 1. Right? So it's what?
It's a covering constraint.
It's a covering constraint. But it's a sort of a weird covering constraint because the left-hand side itself is a variable. I'm choosing which of these constraints I want to cover and which I don't. If this would have been 1 directly, if I had made a statement that I want LP capability, then indeed this would be covering constraint.
If we just write y1 bigger than x1, y1 bigger than x2, it gives the same answer. And y1 bigger than for equation.
Probably. That if, well,
No, because you need each of them to be...
Well, we'll see. It causes a little problem. We'll come to it in a moment. For this particular case, it is indeed true. And we'll see one little thing will happen. Okay. The other one, what about the next 2 constraints? What about y2? That's just, again, by the same thing, x2 plus x4. And y3 is less than equal to x4. So x3 plus x4. Okay. So now the comment was that why not use the variables? So that becomes my problem. So the constraints are this one, this one, this one, and that one. That's the objective in the middle. And then you have the variables xi lie in 0, 1, and the variable yi also lie in 0, 1. So that's my IP. Now the question is, can I put these kinds of constraints, that y1 is greater than equal to x1, and so on. So let's say whether this constraint can be replaced by Is that possible?
It becomes an AND condition.
Yeah, but yeah, fine, that's fine, that y1 must be greater than all of these, but that's sort of okay, right? Because all I'm saying is that if one of them comes to be 1, so the logic behind writing that constraint would be if any of those is equal to 1, then y1 better be equal to 1.
What is that? Doesn't have is not providing that.
Because all of them is providing the LP capability, right? So x1, x2, x3, x4, all of them are providing LP capability. Yes?
Is there a problem with that though?
There is a problem. I want to know what the problem is.
If they're all 0, y1's still going to be 1 because you're maximizing.
Exactly. The problem is that this logically makes sense. It makes sense the fact that x1, if one of them is equal to 1, y1 will be forced to be equal to 1. But the problem is that we are trying to maximize yi's. So we want the reverse possibility to hold, that if yi is equal to 1, if I have made my y variable to be 1, it better push at least some of them to be equal to 1, not the other way around. So that's the problem with this. So really what has happened, really to think about it, is what happened was this way. We wanted a constraint which said this: y1 is equal to the maximum of x1, x2, x3, and x4. This is what we want. The variable y1 must be the maximum of those 4. That's the constraint I want to put into my IP. Now this constraint I can't put because it's not a linear constraint, so I want to linearize it. This is a kind of linearization. This is another kind of linearization. Two different linearization for the same constraint. y1 is equal to max of 4 quantities. This linearization works if I'm trying to maximize yi's. That linearization works if I try to minimize yi's. For some reason, if I'm trying to minimize yi's, then this will fail. Because then I'll put y1 equal to 0, even if one of those x1, x2, x3, x4 is equal to 1. Then I'll have to go using that one. Right? So you have to keep in mind that both of these things are valid approximations, but you just have to look at the context, whether it's maximization or minimization. The true constraint that we want is this one. But this is not a constraint I can impose. And using the fact whether I'm maximizing or minimizing, I can linearize it 2 different ways. All right? What else? So it's just a different example over there. There's one example that I want to talk about. I don't know whether I put it in here. I didn't. But let's go before I go away from there. Any questions? Okay. So there's another one of the problems that's not there in the notes, which is important for a completely different reason, which is ease of solving it. That's not something that we will do in this class, but it's always good to keep in mind that if there is a problem that you can solve which can be solved as a linear program, it's always better to do it that way as opposed to solving an integer program. So here's the problem. It's called the assignment problem. And the assignment problem has the following structure. You've got n jobs and n workers. It could be less number of workers, more number of jobs, and so on, but the classic way in which it is put in is to write it as n jobs and n workers. And there is a weight Pij. This is the value of assigning job I to worker J. And what the assignment problem wants to do is find an assignment. And what's an assignment? It's assigning a particular job to a particular worker, which means that 2 jobs cannot be assigned to the same worker, and 2 workers cannot be assigned to the same job, in such a way that it maximizes the total value. So the problem, the integer program here is very simple. You want to maximize the summation over I going from 1 through n, the summation of j going from 1 through n, of Pij times Xij. And what is the interpretation of Xij? Xij is equal to 1 if job I goes to worker J. And it's 0 otherwise. Yeah, it's a value, so I'm trying to maximize it. I'm maximizing the total value to the system by offering these jobs to these people.
Like the hospital problem.
It's like the, which one?
No.
Yeah, it's sort of like the nurse assignment problem, but not quite, because there we are just trying to minimize the cost of nurses subject to demand. Here we're simply saying that different people come in and they want to solve this problem. And in fact, Ward Witt and one of his PhD students or co-workers are actually starting a company which does something like this in call centers. There are people in call centers who want to work on certain kinds of calls. I'm just imagining people in Apple, because I just had a breakdown with my Apple machine, that there are people who want to just specialize in data recovery versus, do the drudgery of, I don't know, fix airports or something. So there are different questions. Go ahead. The thing is that if you're a Unix user and you want to switch to something that looks like Windows, Apple is close enough. Okay, so the constraint here would be that if sum over I going from 1 through n. Yes, question, just a moment. Let me write down this constraint, I'll be with you. J going from 1 through n of Xij must be equal to 1. This is for all j, taking values 1, 2 up through n. This is for all I, taking values 1, 2 up through n. And each of the Xij takes values 0 or 1. Yes, question.
I didn't quite understand. Basically, you're assigning the job to the workers in the sense. Is there some kind of a price on the job, or is there some kind? What is it?
For now, just think of this as certain. Another place where this kind of thing has been used up is in assigning residents to medical students to residency programs. So Pij could think of jobs as residency programs, workers as medical students, and every student ranks all the different positions that are available. And there's a person who's allocating and wants to make sure that they maximize the allocations that are there. Okay? They're maximizing the value to the system. This is not quite the problem that they were going to solve, because in that situation you have sort of incentive constraints. You want to make sure that everybody is happy. Yeah, this doesn't mean that everybody is happy, because it's possible that somebody was given a very low order job simply because the whole system optimum becomes better by giving somebody else the higher order job. Okay? So what does this constraint imply? The sum from I1 through n Xij equal to 1. What does this mean in words?
Only given one job.
So J refers to worker, so this basically says is that every worker is getting one job. I refers to job, so if you're summing over J's, it means that every job goes to exactly one worker. Okay? So that's an assignment problem. It's a trivial problem, but the reason I want to talk about this problem is it turns out that if, in this particular case, if you relax this problem, meaning that instead of solving the integer program, you solve this problem. So that's a linear program. It turns out that the answer that you get is the same. If you have an assignment problem, the P solution is the same as the IP solution. So for this one, LP relaxation is exact. So that's very nice. Then it means that I don't have to worry about putting those 0, 1 constraints. There are n squared, capital N squared of those 0, 1 constraints. There are a lot of different variables. There are 2n constraints over here. 2n constraints means that there are 2n fractional variables. But what this tells me is that no matter what number of those things are, there's a little bit of LP relaxation is exact as a statement that's not quite correct. The correct statement would be that if the LP is solved using simplex, then you get an integer solution. This is what the correct statement is. Meaning that if you get a corner, all corners of this LP are going to be integers. But it's possible that more than one corner is optimum, which means that anything in the line connecting those two corners is optimum. So if you're not solving it using simplex but using some interior point methods, you might get a point in between, which is certainly not going to be feasible for the integer program. So,
would rounding help in that case?
What?
Would rounding take you to the right solution in that case?
Well, there are techniques available, and
But I mean, in this particular one, if you end up with where the corner isn't the solution, but the face is a solution,
yes.
right? Then would rounding take you to the exact one?
The problem is that you have to, yes, you can round it, but you have to be careful about rounding it. So you have to make sure that these constraints are sort of met, right? You can't just round a variable at a time.
Oh, that's right. Okay, sorry.
Because there are constraints, so you want to make sure that if you're rounding something down, you round something up simultaneously and so on. So to answer that question, there is this thing called randomized rounding, which became very famous by Prabhakar Raghavan and a bunch of other people, where they basically got out techniques by which you're guaranteed to get a feasible solution by randomized rounding. Another possibility is when you get a face solution, there are other techniques available to take you to a corner on that face, because it's a convex combination of the corners, and therefore there must be some way of getting there, and there are ways of doing it. Question?
Is this true of the traveling salesman problem too? Like, isn't that kind of an assignment problem?
Good question, and the answer is no. It's not true. This is not true of the traveling salesman problem, which will come in a moment. And in fact, traveling salesman problem is the canonical integer programming problem. It's probably the hardest one floating around. Okay, all of them are, from the complexity perspective, hard, but from the popularity perspective, TSP is like a holy grail.
But this one is not NP complete.
No, this is not. This
It's
is
not the same class.
what?
It's not the same.
No, meaning that there are other problems other than TSP, which are all in the same complexity class. You can't call TSP as the hardest IP, because there are other ones which are in the same class and so on. Okay, so what's special about this particular problem, that it can be solved, that I know that LP relaxation is exact? One would like to know this. One would like to know what class of problems are there, such that if I formulate an IP, I know that the solution will be the same as the LP solution. If I knew that class of problems, I would try to massage my problems to start looking like those. Somehow approximate it that way, because then I don't have to solve an LP, don't have to solve an IP. Okay, so any of you have seen that before?
Convex hull.
Convex? No.
Convex hull of
Convex hull of everything is convex.
has integer boundaries.
The convex hull of any integer program has integer boundaries.
Not this LP has integer boundaries.
Yes, but why? Why does it have integer boundaries? Well, this is just a restatement of this. The statement that the convex hull has integer boundaries is just a restatement that the simplex will find you an integer solution.
That is why it was.
Right, but why can I just look at this, the LP, and deduce, yes, indeed the corners will be all integers. That's basically what I want to do. I mean, I don't want to keep solving the problem and then discover that indeed it's giving me corners that are integers. I just want to look at this. Yes?
Well, you have equality constraints there that force everything to have a one-to-one ratio.
Well, even if you make it inequality, not a problem. Let's make it less than equal. At most one job to every worker, at most one worker to every job. Still the same thing.
Linear objective. Linear objective.
Linear objective, but so are the objectives in every IP, right? So the thing is that so all of those things are right, but we still needs to be something special about this IP. And if you haven't seen this before, then it's very difficult to discover it here. So I just want to know whether you've seen this idea before. If not, I'll just tell you the answer, because discovering it is hard. So one rule of thumb that works for this is that if you take your linear program, meaning, and you can write it as a network flow problem, if you can write it as you're trying to maximize the flow in some network, then that particular IP can be solved as a linear program. And what is that? What are we doing here? We can think as if we are looking at this network. So here's a network, here are the jobs. There are n of these. And then here are workers, there are n of those. And what I'm trying to do is push in a flow of n units from here. There is a capacity of 1 unit of flow going on all of these edges. Similarly over here, there's a capacity of 1 unit on all of these, and I'm trying to pull out a flow of n units from there. And over here, these edges are going this way. They have a certain value Pij, but a capacity which is infinite. And the same thing happens everywhere here. Capacity is the amount of flow that I can push through that edge. Okay? So what this is, if you're looking at this network, then what I'm trying to do when I'm trying to solve this problem with relaxation here, not with 0, 1, all I'm trying to do is push flow through this network in such a way that the total value is maximized. Okay? Why is it the same thing? Because when I'm trying to push flow from here, a n unit flow and a capacity of 1 unit on all of these edges, 1 unit of flow has to come out of all of these. So therefore exactly 1 unit gets into the jobs. That 1 unit of flow has to be split up into all of these edges, but there's exactly 1 unit of flow going out. I'm pulling out n units of flow from here. There is a capacity of 1 on all of these edges, which means that exactly 1 unit of flow has to be pulled out of each of these worker nodes. So which satisfies that constraint and that constraint. Forget about the inequalities. You're satisfying these two constraints. And since each of these, the total flow that's coming into each of these nodes is at most 1, therefore xij must be between 0 and 1. In fact, in the relaxation you can simply have xij greater than or equal to 0, and it's all the same. Because since the sum of the xij is equal to 1, each of them is going to be less than or equal to 1.
One can get a fractional solution that's equal to the integral solution.
Yes, so but if it's unique, that's what I'm saying, that if you solve this problem by simplex, you will get a corner. And all corners for this particular one will have integer solutions. But it is the case that you can get an optimal solution which is fractional. And when 2 corners are optimum, you can get somewhere in between. So that's why I was removing that. The precise statement is that if you try to find a corner, you will get integers. So in this particular network, it turns out that anytime you can write an IP, you take an IP, you relax it, and then you write this linear program as if you're maximizing the value of a flow in a network or minimizing the cost in a network. Then you're guaranteed that the solution that you'll get by solving the LP at the corners is going to be integers. And knowing this is a good thing, because what it would amount to saying is that a lot of times very hard-looking IPs can be converted into something that looks like network flows. And if it looks like a network flow, it's a linear program, which means that I can solve it much more simply as compared to an integer program. So first thing is that IP equal to LP, or the same as LP, if network flow. But that's not the complete answer. The real answer is that IP is equal to LP if the matrix A, the constraint matrix, whatever is, so you put both of these constraints together, call that the matrix A, is totally unimodular. If you have never heard that word, pretend you never heard it even now. It's not something that we will talk about in class, but it's something that I want you to just be aware of, that if somebody says a matrix is totally unimodular, they're worrying about the fact that they're trying to solve an IP, and they want to get around solving that by solving an LP. And if they're trying to do that, one of the things that they'll be attempting to do is to show that the constraint matrix is totally unimodular. For networks, yes?
Yeah, Professor, what's the meaning of the objective function in here? You said it's network flow, but it seems that the flow through the network is always n.
Yes, but the value of the flow is different.
Oh, okay.
Because depending upon which particular edge that you choose from here, you get different values. Out here, it's always n. Out there, it's always n. But the value that you're getting is from routing in here.
what's the practical meaning? I mean, inside the value changes, but coming in and out is always the same.
Yes, so what does that mean? I mean, you can look at a cell phone network, and the total number of users on this cell phone networks are always constant, but depending upon which cell tower you send to them, they get better or worse reception, which means that the value that you get from the system is very different depending upon how you route the traffic, even if the total traffic remains the same. In more practical cases of like jobs and workers, it depends on how much they like a particular job. You get more value out of that. Okay, so we'll do TSP in the afternoon. Let's break here.
Well,